Okay, good morning, everyone. I think it's time to get started. So thanks for attending this last day at EUSIPCO. It's my great pleasure to introduce Professor Simon Doclo from the University of Oldenburg in Germany. Simon received his PhD at the KU Leuven in Belgium. We were actually close colleagues for a number of years. We overlapped there. I still remember the nice time we had at many of the conferences that we attended together, so we really had a lot of fun. After that, Simon was a postdoctoral fellow at the KU Leuven, also at McMaster University in Canada. And from 2007-2009, he was a principal scientist with NXP Semiconductors in Belgium. And then in 2009, he became a full professor at the University of Oldenburg in Germany. And he's also a scientific advisor for the Fraunhofer Institute for Digital Media Technology. The research interests of Simon evolve around audio, speech, as we will hear today in his talk, so hearing aids, noise cancellation, speech enhancement, and so on. Simon received a lot of Best Journal Paper Awards from EUSIPCO as well as IEEE, and also the VD Information Technology Society. He was a member of the IEEE SPS Technical Committee on Audio and Acoustic Signal Processing, also the EUSIPCO TAC on Acoustic Speech and Music Signal Processing. He was involved in organizing several conferences, also associate editor for numerous journals, and currently he serves as senior area editor for IEEE ACM transactions on audio, speech, and language processing. So, yes. I think that concludes the introduction. So it's a real honor to have Simon here today. So looking forward to your talk.
Okay, thank you very much for your kind introduction, Geert. We indeed had fun conferences. I would also like to thank the conference organizers and the plenary chairs for inviting me to give a presentation here at EUSIPCO. And as the title states, the talk will be about model-based and learning-based approaches for speech enhancement and source localization. And I will also focus on so-called hybrid approaches that merge the advantages of model-based and learning-based approaches, so the interpretability of model-based approaches and the performance of learning-based approaches. This talk will mainly focus on speech communication applications. This could be, for example, mobile phones. Most mobile phones look a bit more fancy than this one on the picture. But also for hearing aids, or more in general, hearing assistive devices for normal hearing people, assisting their communication in difficult environments. And last but not least, also for smart speakers. And the main objective in all of these applications is that somebody, the user of these devices, wants to communicate with somebody. Target speaker in an environment, but in this environment, also acoustic disturbances are present. This could be, for example, some ambient noise, some radio playing. This could be other competing speakers in the room, or this could also be reverberation. These are acoustical reflections against walls and objects in the room. And all of these acoustic disturbances, they degrade the speech quality and also sometimes the speech intelligibility of the recorded microphone signals for speech communication applications, and also speech recognition performance for voice-controlled systems. Although the talk will mainly focus on speech communication and not on speech recognition. Something is going wrong here. There's 3 screens with a mouse, and the mouse should be on the correct screen. Yes, thank you. No. Yep, good there. Okay, so the main objective, of course, of speech enhancement algorithms is to extract the target speaker from these noisy and reverberant microphone signals. It could be done, for example, with the goal of just reducing the ambient noise, reducing the reverberation, or for example, doing blind source separation and then picking the correct target speaker from the output signals. However, what I want to really mention is that for speech communication applications, there are some important requirements which will also determine which of the algorithms are most suitable for these applications. First of all, of course, we would like the output signal to have a very good quality, so that the speech distortion is quite low. But also for these applications, online processing is of course really relevant, because these applications have to work in real time. So low latency requirements for the algorithms are quite important. Overall, also in different environments, these applications, these devices have to work, so they have to generalize and be robust to varying, even also time varying, of course, acoustic environments with moving sources, moving speakers, maybe even moving microphones. That means, as we will see, that also maybe the most fancy machine learning-based algorithms that are typically acausal, so batch, that also sometimes don't generalize so well to these environments, are not always the most suitable for these applications. And last but not least, also in battery-powered devices, for example, like hearing devices, computational complexity plays a large role. So we want to have low complexity, low latency algorithms for these applications. If you look a little bit at different kind of classes of algorithms, of course we have single microphone algorithms that only use spectrotemporal information of the speech signals. Most devices nowadays also have multiple microphones, so we can use some spatial processing, exploiting the spatial diversity, the different positions of the sources. But if you look at three classes of algorithms that I will also discuss more in detail, we have model-based algorithms, and this is still in general, not only for speech, but for different areas, where we have a certain signal model, and you want to estimate the model parameters, and then put it in the speech enhancement algorithm, in this case. Typically, in these kind of approaches, there are some assumptions that need to be satisfied, and well, as they are not satisfied in practice, sometimes these approaches don't work that well. On the other hand, although it's not really on the other hand, but we also have learning-based approaches where a neural network is trained by minimizing a loss function and then is feeding this in to enhance the speech signal. I would say also there are actually some kind of assumptions, but there may be a bit hidden in the training data that is used to train the neural network. And then you also have hybrid approaches, although there's many varieties of these hybrid approaches that merge such model-based as well as learning-based approaches, where maybe some parameters, some filter structure is imposed on the speech enhancement algorithm, and then the parameters, the filter parameters, the filtered quantities are being learned in an end-to-end fashion by the deep neural network. And I will also give some example and play some audio files for such a certain application in the context of hearing aids. I also noticed, it's more like a general trend, there is some nice overview paper in the proceedings of IEEE this year, and I think also at 10:30 there's a session here at EUSIPCO Advances in model-based deep learning, so it kind of also really fits into this trend. In this presentation I will focus mainly on hearing devices or more general assistive listening devices, but most of the techniques I will present are also applicable to other speech communication applications. It will, as I already mentioned, mainly focus on online approaches, only using past and current and past information, and will mainly focus on multi-microphone noise reduction, although at the end I will also mention different kinds of approaches that can be used for localizing sound sources. And last but not least, I will also discuss the benefit of including some spatially distributed microphones, so-called acoustic sensor networks, as one can imagine that the hearing device in this case also works together with other microphones in the room, spatially distributed microphones, such as mobile phones or microphones on a laptop. And just to mention this of course increases the variability of the acoustic scenario, since of course typically the position of these external or distributed microphones are not at all. Let's now start with first part, multi-microphone speech enhancement. And I want to set the stage a bit and introduce the scenario there. There will also be a couple of equations in the next couple of slides, but they are quite general, not only focused towards speech or audio community. So first of all, we have, of course, a listener with, in this case, a binaural hearing device, meaning there's a device both ears, the left and the right ear, and that the person here wants to talk to speaker or person, target speaker in a reverberant room. So there are some reflections against walls and other objects in the room. Of course, I've already mentioned there could be multiple speakers, there could be an interfering speaker, there could be some noise in the room, which we would like to reduce as much as possible. And we will also consider in some parts of the talk some external microphone, here abbreviated as EMIC, where there could be just a different positions, of course, typically unknown positions in the room. Speech enhancement is typically performed in some kind of transform domain, although also some time domain algorithms have been proposed, of course. And this could be just a very simple fixed transform, like a short-time Fourier transform domain, but also more recently, of course, learned transforms have been used, although I would say the debate is still a bit open in this area. What are the best transforms to be used, especially in reverberant environments and also where the algorithm has to work in different contexts. So if we would have a look at just the EMT microphone, the EMT sensor signal at the K frequency bit and L time frame, it can actually just be written as a convolution of the clean speech signal S and the acoustical transfer function H of M, even in the frequency domain. And just to mention this, if somebody doesn't know, in the audio fields, this multi-pad propagation or the reverberation, it involves thousands of taps. So it's not just 4 or 5 taps, it's thousands of taps. So it's not as easy actually to model and also to remove. Typically, the speech component in one of the microphone signals, when the EMT microphone signal is then still split into 2 parts. One part which is related to the direct, the early reflections, and one part which is more detrimental actually to quality and also intelligibility, the late reverberation. Now, if you put everything together just in the vector, we have here all the noise in the reverberant microphone signal, so the observations. We have the desired signal, the clean speech signal in one of the microphones, and we have here this vector A. Many people will know this kind of model also in different applications, sometimes called steering vector. Here it's a little bit of an extension. We typically call this the relative transfer function vector, relative early transfer function vector. So it's actually an extension of such a plain steering vector towards reverberant environments, so taking also into account some of the reverberation, some of the reflections in the acoustical environments. And then we have all the disturbances, and I've just put them together in this vector U, late reverb, interfering sources, and ambient noise. We have a little bit closer look at the specific application, just to make it a little bit more visual. I've plotted here the relative impulse responses, so the time domain equivalent of the relative transfer function for the specific application with hearing aids, where this is just the relative impulse response between the right and the left microphone on this hearing aids. And obviously, as you can see, this is one, not yet, but this is plotted for 3 directions. And as you can see, for the different directions, of course, there's different directions of arrival that can be interpreted from these relative impulse responses, but also head shadow effects and some kind of early reflections are there, so it's not just plain impulses. Although, as I will also say in the last part, or the last couple of slides, these relative transfer functions, since they encode the direction of arrival, they're very useful features also for doing direction of arrival, sound source localization. So, given this model, actually speech enhancement is pretty easy, right? We have our noisy and reverberant microphone signals. We just have to estimate x1, this clean and non-reverberant signal in one of the microphones. Now maybe already some people wonder why do we estimate the signals in the microphones, the speech in the microphones. Actually, it has quite some advantages. For example, for the hearing aid application, if you estimate speech in the left and the right microphone, you also directly preserve the spatial impression, the spatial cues of the target speaker. So it has actually quite some advantages, although it even makes the problem maybe a bit simpler, it also has advantages. Now, on a high-level distinction, of course, you can say we estimate the speech signal with a highly nonlinear, a large function f of y. And it has been shown also for multi-microphone speech enhancement in a nice paper from the group of Timo Gertman, that this has some advantages to really use this nonlinear function. However, as a disadvantage, it's typically less interpretable, and also one requires typically larger neural networks to estimate such a function. Therefore, especially for low complexity, low latency application, typically still simple, I would say, linear filter is being used, a filter and sum structure, where you just have double your emission times the input signals. As we will see also for this linear filter, we can then choose to impose a filter structure or not, going towards hybrid approaches. Although typically a simple linear filter is used, and maybe some people are now disappointed at this talk, there are, of course, different ways to estimate the coefficients or the parameters of this filter. So we have, let's say, traditional statistical estimation methods. I don't like the word tradition, actually, where typically some model assumptions are being made that are not always satisfied in practice. On the other hand, there's learning-based approaches, and in this talk I will mainly focus just on the supervised learning-based approaches, a loss function between them. Last but not least, up to now I've only covered so-called single-frame approaches, where this was only a single frame of data. Typically also one can use multiple frames at the input, and this is not just a simple extension to use multiple frames. In this application, it also allows to distinguish between the temporal context you use, number of frames, times the frame length, and the latency in these applications. Because if you use here small frames and a multiple of them, you can actually achieve very large, very low latency just by design. And this is actually a bit related, of course, to what most people also know as partitioned block, partitioned convolution, also showing, and as I will see later, that also these traditional signal processing concepts are not that in the age of deep learning. Now focusing a bit on this, this linear filter, I would say the workhorse algorithm, the typically used filter and sum-based algorithm, is a so-called parametric multi-channel Wiener filter. And basically the idea is that you estimate the speech component, you estimate this speech component in one of the microphone signals, but you can also trade off between speech distortion and noise reduction. As most of you will probably know, this multi-channel Wiener filter can be written in terms of the covariance matrices of the speech and the undesired component. So basically, just to implement it, you just need to estimate these filter quantities. I call them model parameters, filter quantities. By plugging in this model, this signal model, it has been shown since quite a while that this multi-channel Wiener filter can then be decomposed into a so-called minimum variance distortionless response beamformer, MVDR beamformer, and spectral pose filter, where the MVDR beamformer is just the spatial part, the spectral pose filter is the spectral-temporal enhancement. Again here, these quantities, for example in the MVDR beamformer, depend on covariance matrices, this relative transfer function, and basically one just needs to estimate these quantities and one can implement these filters. And as I will show in the next couple of slides, there's traditional methods to do this, typically requiring assumptions, and supervised-based methods, where I will show a specific example. Just one slide on this multi-frame extension, because I kind of like it, especially because there you can, I wouldn't say trade off, but distinguish really between the temporal context that is being used and the latency of the processing, which is quite important in these applications. It has also been shown that if you look at this multi-frame vector, that it can be decomposed into its temporally correlated parts and temporally uncorrelated parts, with the so-called speech interframe correlation vector. Or in general, for people not working on speech, it's just a correlation between the spectral correlation in a certain frequency bit, or the temporal correlation in a certain frequency bit, between a certain frame and all the previous frames. For speech processing, it can be analyzed and can also be interpreted that this is depending on the sound that is being produced. For example, for voiced sounds, A, E, I, all quite correlated, you will see quite some coefficients that are not zero in this interframe correlation vector. For more unvoiced sounds, it will be more like 1, 0, 0, 0, not so much correlated. That also means that this kind of vector is very time variable, because it will change on the order of 20 to 30 milliseconds. So it's also not too easy to estimate, and that has also been shown by, I would say, traditional estimation method. It's quite hard to estimate this speech interframe correlation. Now, plugging both the spatial model as well as this spectrotemporal model together, we have actually the multi-frame signal model, and it's basically just, again, a steering vector that needs to be estimated, which can be shown to be a Kronecker product between the spatial component, this relative transfer function vector of the target speaker, and the interframe correlation vector. Both of them are actually time varying, but there's a difference. Typically, people don't move on the order of 20 to 30 milliseconds, except if they would be running around here on the stage. Yeah? But both of these vectors are time varying, and they will have to be estimated, maybe together, maybe separately. So let's get a little bit closer into this estimation. If you have, again, traditional, and again, if you have traditional estimation of these parameters that I mentioned, they typically assume some kind of model. They have some assumptions that need to be satisfied in practice. And I don't want to go into too much detail. It is very specific maybe to the speech field or to the audio field, but just to give you some impression, for example, for covariance matrices or PSDs, it's assumed sometimes that the undesired component, the noise, is more stationary than the speech, or maybe that the reverberation is diffuse. For the relative transfer function, sometimes it's assumed that the source activity is known, or that we have anechoic propagation, and actually, as in all assumptions, they're actually wrong. They're not really satisfied in practice, so if you use these kind of methods, they will also have this disadvantage of having to require these assumptions. I haven't even talked about the speech interframe correlation vector because I think there have been many tries in traditional approaches, but all of them have kind of failed to really estimate this kind of quantity very accurately. On the other hand, of course, we have supervised learning-based approaches, where, as I already mentioned, mouse again, where a neural network is being trained, training data, and minimizing a loss function. Typically, in our field, this loss function is again in the time domain, so after the reconstruction. And then either the filter parameters directly are being estimated, or some filter structure is being imposed. And all of this is always then trained in end-to-end fashion, also the filter coefficients, as well as the parameters. So that's what I mentioned. I would say there's two fundamental options here for this kind of approaches, which are trained in an end-to-end fashion, is to just say, okay, there's a linear filter, let's just estimate these parameters. Multi-frame or not, large or small, we'll just estimate them. How to interpret them, I don't know, but they're physical coefficients. Or we can also use hybrid approaches where we say we impose a certain filter structure. For example, this multi-channel reader filter structure, or the MVDR structure, and we actually estimate the parameters, the quantities of these filters, for example, the covariance matrices and the RTF vector, in an end-to-end fashion by integrating the differentiable multi-channel reader filter or MVDR filter into the processing function. I put some recent references. There's quite some interest actually in this field because it's also then more interpretable, to interpret also these matrices, to interpret this RTF vector. So maybe if something goes wrong in a very strange situation, you could still intervene, which is more difficult in a nonlinear function or even just by estimating the filter coefficients directly. It also has to be a bit noticed, and it's a note I want to make, that even if we have these covariance matrices and this RTF vector, it could be that it's not really the true oracle covariance matrix or the true oracle RTF vector. Although when it's the question what is oracle covariance matrix, one also has to make choices. It's just the best possible covariance matrix, the best possible RTF vector, minimizing this loss function for the specific application of speech enhancement. Also, in other applications, in sound source localization, there was a paper calling this then surrogates covariance matrix, surrogate RTF. Of course, I don't want to go into detail there. There's a lot of neural network architectures every week. There's a new one, I think, right? But in this field, maybe 2 years ago, a lot of LSTMs, also transformers have been used. Temporal convolutional networks we've been using in our group quite often. If you want to reduce computational complexity, often GRUs, gated recurrent networks, are being used with skip connections. But I don't want to go into too much detail. You basically take the network that you want to use for your application, for your complexity. Also in loss functions, I don't want to go into too much detail because it's quite specific for the audio and speech field. But of course, one can use mean squared error, which is never used anymore, I would say, here in the speech and audio field. A very popular one is, for example, scaling variant signal to distortion ratio, or some more psychoacoustically motivated loss functions. But this is becoming very specific, so I don't want to go into details for the general context. So this was a bit general theory. I think it's even applicable to almost all fields. Let's now go to a specific application, where I will discuss one of the algorithms and also play some sound files for these binaural hearing devices, using a supervised learning-based approach, a hybrid approach, and comparing it to a direct filtering-based approach. So in binaural filters, just a small extension, you have two hearing devices, so we also need two filters, but basically the concepts remain the same. Just for information, for people who are maybe a bit interested or familiar with this as the features, we could have used just the spectrogram, but we used noisy magnitude and cosine and sine of phase to get rid of some phase wrapping or phase ambiguity problems. And then there were two approaches which we analyzed and compared. So directly estimating these filters, just these W's, these coefficients directly to the filters, or imposing some filter structure where we have DNN estimating the inverse covariance matrix directly, and the DNN estimating this speech correlation vector, both spatial as well as spectrotemporal information, and both are trained jointly on a loss function in the time domain. And as a loss function, we use this so-called combined mean absolute spectral error after the reconstruction, where you can distinguish a bit between ambient difference. On data settings, also there I will not go too much in detail, because it's also specific to this field, but as in all fields, of course, we have to make sure that training and test sets are quite different and quite diverse. Also in our field, there have been quite some challenges in the last year, international challenges, like the deep noise suppression challenge, DNS challenge, or so-called clarity enhancement challenge, especially for hearing devices. And this is of course nice because you can use these data sets for all training and also for uniform testing. And basically also we always make sure that the ranges of course of SNRs and also the reverberation time are quite different between the training and the testing in order to make it robust against these environments. What I do want to focus on a little bit is the specific setting for this multi-frame filter, which uses just for the SDFT domain, has 8 millisecond frames and 2 millisecond shifts. So that's what I like about these multi-frame approaches, that they also are low latency, or you can make them low latency, at least by design. There have been other low latency approaches here, also by people in the audience, which for example use asymmetric window designs or really partition convolution. And that's something I really want to stress, and I already mentioned that also these old-fashioned, these old signal processing ideas, they're really not that in the age of deep learning, but especially for low latency, low complexity applications, they're becoming more relevant, or they're being almost sometimes reinvented, it seems. Just for your information, at DNS we used temporal convolution networks and some visual settings. If you have a look at the first objective performance metrics, and these are typical metrics used in our fields, so-called PESC, conceptual evaluation of speech quality, and frequency-weighted SSNR, FW SSNR. And there what I show here is for this test set, the performance of 3 algorithms. The blue bars are just single-frame processing, so just a single frame. Then the orange and the green one are this multi-frame processing. And one can clearly see that it's a small but still significant benefit of using this multi-frame processing versus single-frame processing. And then one can also see that by imposing just this MVDR structure, one also gets still a small but significant benefit versus not imposing the filter structure. It's not a huge difference, but it's still significant. Let's now finally listen to some audio samples. Yeah? So what I will play here is a noisy signal and then enhanced signal with these 2 approaches. And obviously there's not too much difference between the approaches, but maybe you can focus on the speech quality, the speech distinction. So let's first listen to the noisy speech signal. This is not good quality. We tested it, but I cannot play this because it's, I don't know what
it's supposed to be noisy, no?
It's supposed to be noisy, but there are some distortions, as you can hear. I heard.
In solitude, he lost his momentary charm, become oppressive. Did many bodies go away near him? She radiated warmth and good fellowship. We can die too. We can die like real people.
So, sorry for the Scottish people, but the bagpipe was a noise. So let's listen to the process with direct distinction.
In solitude, he lost his momentary charm, become oppressive. Did many bodies go away near him? She radiated warmth and good fellowship. We can die too. We can die like real people.
And now with this hybrid approach.
In solitude, he lost his momentary charm, become oppressive. Did many bodies go away near him? She radiated warmth and good fellowship. We can die too. We can die like real people.
So as you can hear, I hope at least, bagpipe was reduced quite a lot, and also distortion is quite okay in these kind of approaches, I would say, especially when imposing this NVDR structure. Now, of course, generalizability, robustness in real environments is quite important, so I asked my students just do a recording in the lab, play around a little bit, and it's untrained scenario, it hasn't seen sometimes of these noises, people are also moving a bit, and let's listen how this is.
Welcome to the demo. The goal of the demo is to show you how stable are deep learning algorithms can be exploited for speech enhancement. That's why we created this noise environment where this basketball is bouncing over and over again. And this makes it difficult to hear the assessment. The signals that you hear right now are the ones from the hearing aid device. So that's the process condition. Switching on our output. There's now here a significant amount of noise reduction. Well, not or only slightly distorting the speech signal. The algorithm that we use to achieve this is a combination of deep learning and also multi-frame multi-channel processing. And now let's switch to SDC.
You are now again listening to the unprocessed signals of the hearing devices, but now with the cajon as a noise source and a different target speaker coming from a different direction. Again, this acoustic scenario makes it difficult to clearly understand me, and that's why we consider again our speech enhancement algorithm. Switching on our deep learning-based algorithm, you hear how the background noise is attenuated. This demonstrates how well the neural network generalizes to unseen speakers and noise sources, and then is able to adapt to new scenes very quickly.
So this is just to give you an impression what is possible nowadays, real-time algorithm, real-time processing online. How large are these networks now? I would say maybe still a little bit too large to be implemented in hearing aids, but still not huge. It's not like ChatGPT with billions of parameters. So if you look, just to give you a little bit of numbers, it's 5 million trainable weights. It doesn't say all, of course, how difficult it is to implement it in practice on devices. But at least if we test, for example, the so-called real-time factor, we can see all of these algorithms are real-time capable. And of course, by imposing some filter structure, so this NVDR structure, it's a little bit more expensive because there are some linear algebra operations. And although I didn't really mention this yet in this talk, in the recent paper, we actually also checked different matrix structures for this NVDR filter. So for example, we know covariance matrix is positive semi-definite, so we actually have some cholesterol decomposition, which we actually estimate using a neural network. Or we also tried out, for example, template structure, and so we have a Van der Waals matrix, which is actually learned by neural networks. And I find this quite cool, to be honest, especially with the background from the Leuven group, that even in the age of deep learning, we can also try out different linear algebra operations, different structures, together with deep learning in a supervised way. Now switching back, now we have supervised learning, hybrid approaches, you've heard what is possible. I do want to present also one of the traditional approaches, for estimating relative transfer function vector. And the assumption, one of the assumptions that is made here, that we have spatially distributed microphones available. So we have hearing aids and some microphones actually in the room, which are at a certain distance. And we also assume something for the background. Of course, the idea of merging hearing aids with external microphones is not new. There have been many studies trying this out, both for noise reduction as well as for localization, or for example, enhancing these spatial cues in the hearing aids. And one of the algorithms I would like to present, and it's only one slide because it's extremely simple, but it makes one crucial assumption. The crucial assumption is that the undesired or the noise components in the distributed microphones, in the external microphones, are uncorrelated with the noise components in the local microphone in the hearing aid signals. And this may sound at first a very restrictive assumption, but basically it's almost satisfied if the external microphone is about 40 to 50 centimeters from the hearing aid, and we have babble noise, spatially distributed noise, which is actually a scenario that is encountered in many scenarios. If you go to the banquet, for example, there was spatially distributed noise, definitely there, and if you would have had an external microphone on the table at a certain distance, this could have helped us actually in the speech communication, if you wanted to communicate at least. So, what is being done here to estimate this relative transfer function vector? Basically, you can have the covariance matrix here. It's my problem with the mouse. But anyway, I will not point in this green column, which is actually one of the columns of this covariance matrix related to the external microphone, can actually be shown, at least in theory, that it is just a scaled version of the RTF vector. Just by just taking this column, normalizing by the correct elements, we actually have an estimate of the relative transfer function. And it has been shown also in simulations, we had quite some papers on this. It's a very low complexity algorithm, just correlation, it's almost too simple to present here, I would say. But in practice, for this specific application, it can yield a very good, sometimes even better performance than state-of-the-art approaches. For example, based on generalized eigenvalue decompositions and requiring an estimate of the noise covariance matrix. So let's play a demo also of this kind of algorithm. What is possible there?
So first, let's listen to the unprocessed hearing device input signals, where we not apply any noise reduction, but where the spatial perception is correct. That means you're localizing it correctly now on the right side. You are able to follow my movement by listening to my voice, and you're now localizing it correctly on the left side. The overall goal now is to reduce the undesired background noise while preserving the spatial impression of the In the system, we not only have access to the head-mounted microphones of the hearing devices, but also to an external or remote microphone that is attached to the speaker, for example. One idea is to just stream the external microphone signal to the hearing devices and play it. By doing so, as you can see, we can acquire a much higher signal-to-noise ratio, but the spatial perception is completely gone. You're not able to follow my movement anymore by listening to my voice, and you're not able to localize me correctly on the left side now. To counter this problem, we are now combining the external microphone with the head-mounted microphones and process all microphone signals together in the binaural noise reduction algorithms. As you can hear by doing so, we apply a significant amount of noise reduction to the microphone signals and preserve the spatial impression of the acoustic scene. That means right now you're localizing me correctly on the left side. You're again able to follow my movement by listening to my voice, and are now correctly localizing me on the right side.
Okay, just to give you an impression of what is possible with a rather simple algorithm, and of course, there's a typical question: what happens if the microphone is not in the shirt? It also works if it's a little bit further from the speaker. What happens if you have multiple speakers? It will actually enhance all the coherent sources, but if you would be in our lab, I would be happy to also show you this. We also have extensions for multiple external microphones, for multiple competing speakers, also to preserve the binaural cues. There are some enhancement algorithms, and if you're interested in this field, we recently published also a publicly available database with more than 1,500 pulse responses and recordings for these kind of scenarios. Okay, so this concludes the part on speech enhancement, multi-microphone noise reduction. In the last 5 minutes, I would also like to make the same kind of exercise, but quicker, of course, for sound source localization. So also there we have model-based approaches, learning-based approaches, and also bringing these things together in hybrid approaches, merging the advantages. Sound source localization, I would say, is almost a simpler problem. We want to localize the sound sources in the scene, or sources in general in a different context that you're working in. If you look at model-based approaches, a lot of them, I would say, they compute some analytical function, called spatial pseudospectrum, typically based on some maybe steering vector. In this case, it's then called anechoic transfer function or anechoic relative transfer function vector, which are defined for certain angles. We could have beamforming approaches. I'm not sure. It is also used in other areas. It's in our area called steered response power, where you just steer a beamformer in different directions and see where there's most power. You could have a very popular and good subspace-based algorithms like EUSIPCO or ESPRIT, or also you could just have simple transfer function matching-based approaches, which we've also used in our application. In speech, of course, in audio, it's a very broadband signal, from 100 Hertz to 8 kilohertz. So we need some kind of frequency integration or fusion mechanism that there are many proposed. The main thing actually that I want to stress is that in all of these model-based approaches, they can be computed for any microphone geometry. So they're very flexible towards different array geometries. And there's a part in this spatial spectrum which is related on the signal, the covariance matrices, or the noise subspace, and there's or the estimated RDF vector. And there's a part which is just dependent on the array geometry, and so it's very flexible to compute. We've also tried this out with, for example, this application where we have a hearing aid again, an external microphone. On top, you see this figure, and there was a source moving, and also with this rather simple spatial covariance method, which is this correlation, we can actually estimate and track the DOA, the direction of arrival of the sound source, quite well. On the other hand, we also have learning-based approaches. I would like to point you to a very nice overview paper, I think spanning 200 papers in the Journal of Acoustical Society of America, which actually discusses these learning-based approaches. But basically, what happens is that you just learn the relationship between some features, could be spatial features, could be just a spectrogram. You learn the relationship between these features and the direction of arrival or direction of arrivals of multiple sources, either in the classification context or regression modes. Again, different neural network structures have been proposed, quite popular for multi-source. The DOA estimation is convolutional recurrent neural networks, but also attention-based networks are very often used. Just a bit of publicity, we also had a paper here at EUSIPCO using, for example, periodicity degree features for speech-aware DOA estimation. The main point I want to make, and I guess it is realized by most people, is that if you have these supervised learning-based approaches, the training data you train these networks on is implicitly based on the underlying array geometry. So it's learned for one array, and then if you use it for another array, it's not as simple as for this analytical function where you can just plug it in and use it. You would have to retrain it. Although also there is work on so-called geometry-aware or geometry-dependent even DOA estimation, also speech enhancement. And also at the last EUSIPCO, we've proposed the first very simple technique where we just use the array geometry as an extra input. But at the moment, we're also working on conditioning this network in a better way, for example, using film. And then also, of course, there's hybrid approaches. Also in this area, there's a trend towards merging these model-based and deep learning-based approaches, where we merge the advantages of both kind of approaches. And they've been shown actually by some people that they are more flexible at a lower computational complexity. So that's maybe also the main story, take-home message of this lecture. If you want the best performance, you can use the huge neural network, everything will work fine. But for these kind of applications, low complexity, low latency, I think, at least in my opinion, it makes sense to also go towards these hybrid approaches that have an integration of models in deep learning. Just some examples here in the sound source localization field. There was some work to do end-to-end learning of some time frequency masks for signal-aware DOA estimation using a model-based technique, namely the weighted state response power methods. And in another field, I actually also recently found this paper where there was some deep learning aided subspace methods. This was not in the audio field, but it would be interesting to try this out, I think, where there was root music, because this is a differentiable technique, actually, which was integrated where in an end-to-end fashion, the covariance matrices, which are required for music, or in this case, root music, are being learned. So in a sense, it is very similar, I would say, to this deep multi-frame MVDR filtering, where also some covariance matrices were learned to be estimated for the context of speech enhancement. Here they would be learned for DOA estimation. Okay, this brings me to the summary or the conclusions. What I've shown you or talked about today were model-based and learning-based approaches, especially in this context of acoustical enhancement, speech enhancement, but I think they're also applicable to other areas. In my opinion, at least for online, low latency, low complexity applications, hybrid approaches, they could have some benefit, or they have some benefit, and because we could merge interpretability of the model-based approaches without having to perfectly satisfy the model assumptions, and having a very good performance by being trained, for example, on the real data using supervised learning. And what people have seen, and there are quite some publications on this now also showing this, that they tend to generalize better to more dynamic and unseen situations, and that they're especially valuable or useful for these low complexity applications. If people would be interested to work in this field, what are, say, challenges, or we can also call them opportunities, of course. What is the optimal trade-off between latency, complexity, and performance? Also good robustness there. I think both from a theoretical point of view as well here from a practical point of view, that's still an open question. How to best integrate and merge these models with deep learning is also something that is still open, I think. There have been many possibilities, many options tried, but what is the best one? Specifically for this field, how could we generalize this, that also these algorithms will work for different geometries, different array geometries, going towards microphone array geometry independent, or at least aware algorithms. I think that's a very interesting research direction. And something I didn't touch upon is also, I talked mainly about supervised algorithms, but I also think that unsupervised and semi-supervised algorithms are also a very worthwhile direction to look in, both for speech enhancement as well as for source localization. Of course, this work would not have been done without my PhD students, so former and also current PhD students. Also want to thank the funding sources, mainly in Germany and from the EU. And thank you very much for your attention. And I'm now open for questions.
Questions?
Thank you for your really very interesting talk, Simon. I would like to understand better when you explain or the first video, which is model-based, the deep learning. Just in the first video, I have understood that you used the deep learning approach. That I could understand if the neural network is estimating the covariance of the undesired and also the relative transfer functions all together?
Yes. So this was maybe not clear, but this video that I played, this was exactly this kind of scheme. So as you mentioned and asked, and here we have two DNNs, temporal convolution networks, and there this undesired covariance matrix, actually the inverse of it directly was being learned, and this relative transfer function vector, steering vector, but both in a multi-frame context that was being learned, but not separately. We didn't have, for example, oracle covariance matrices or oracle RDF vectors. It was learned directly, it was learned in an end-to-end fashion based on a time domain cost function. Yeah. And that's what we then saw. So Also the training material, it was localized sources, yeah, and it was also the test, although people were moving a bit, but also for diffuse noises, which generalize quite well as well. But that's really the technique that is being played there, that you've heard.
Other questions?
Thank you for the nice talk and the nice summary. I also have a question regarding this setup. Did you actually check whether the learned steering vector is a valid steering vector? Because I guess you're not training on an MVDR cost function, but on an SI, SDR or something.
It depends what you call a valid steering vector. So as I said, this is typically not in our context here, just for example, pure delays, which would depend on the source position and the microphone geometry. So it's a bit of a philosophical question almost. What is the true oracle steering vector or the true oracle covariance matrix? What we can do is look at this steering vector and extract, for example, DOAs, or look a little bit at, for example, spectral correlations, which is then can be interpreted as being, well, what is correct, at least interpretable. That's it.
But did you do that?
Yes.
So did you actually find the DOAs inside of the steering vector? Yep. Okay, that's good, thank you.
For the temporal correlation, I will not comment. That was more difficult because that's what is the oracle.
Other questions?
Thank you, Simon. Very nice and instructive talk. I was surprised that you did not say anything about voice activity detection in your talk, even though I could hear some irony in your voice when you said that estimating the covariance matrices is you just have to do it. But in practice, of course, it's not so easy if you don't have a good VAD. So the model-based approaches really depend on the success of your VAD.
Yes.
And if you think about it, the VAD could be, you could interpret it as some sort of supervised approach that you apply in a model-based speech enhancement scheme where you tell your algorithm when you have noise only, when you have speech plus noise. But I don't think we've been looking at it like that in our community, that actually bringing in an Oracle VAD or an externally learned VAD is actually a way of imposing a supervised strategy onto, for example, a multi-channel Wiener filter. Could you give your view on how voice activity detection fits into this model-based versus learning-based approach, and shouldn't we consider the traditional methods also as being supervised by if we use pre-learned or Oracle VADs?
Yeah, sure. Thanks for the question. Of course, as I said, what is hybrid? How do you merge these things? That would be, I would say, an almost straightforward way of integrating one block, because it would be then, well, the different possibilities. You could have a VAD, or a so-called speech presence probability, which is just trained by itself, and then you use it, for example, for estimating covariance matrices. Actually, one of these techniques, mouse-based dual beamforming, is more or less doing this. Yeah? You could also, of course, think, and that's, I think, sometimes maybe better, to train everything, I mean, up to the end to end, you have certain goal, speech enhancement, with whatever loss function, and then maybe also have the VAD as one block there, or the speech presence probability. That's maybe a bit more specific for everybody, but it's probability saying how much speech is present in a certain frequency, so a certain mask. So, can definitely be done. That would be a good approach.
And related to that, when you design your training data set for the learning-based approaches, is it only examples of noisy speech and clean speech that you provide, or do you also provide examples of noise only? Is that information that could be used by your learning algorithm?
Yeah. So of course, in general, I think to make it a bit, designing your training set is crucial and is very important. And of course, the more realistic, first of all, it is, the better. So I think also in our community, people started with a lot of simulated data, but of course now also going towards a lot of real recorded data, at least we did some data augmentation. Also, they're just providing noise. Actually, I don't think we've done this. It didn't appear to be maybe so important. But of course, it can be done, but then, of course, as a goal, the training target would be 0, right? But we didn't see this as so important, but could, of course, definitely be performed and tried out.
Thank you.
Thanks a lot.
Hi. Actually, I also have a question. In one of the first slides, you said there's a highly nonlinear dynamic from the sound scene to the microphones. And I'm wondering what is that? Because from my understanding, sound waves add up linearly and also propagate linearly.
Yeah, so that's not what I meant. Maybe with highly dynamic, I just mean that people are moving in the scene, yeah, or running around. For example, you saw in one of the demos there was somebody moving, and you're completely right that most of the propagation, say almost all propagation, acoustic propagation, can be considered quite linear. There are some non-linearities, but I think they're negligible. So that's not what I meant with highly dynamic. I didn't mean dynamic non-linear system or something. I just maybe a more dynamic acoustic scene, so where things are moving, people are moving. Could even be the microphone which is moving if you have these external microphones and you don't know the position. So that's the only thing that I meant. And that, of course, if you read it, for example, to the training set, can be quite difficult because you cannot cover, I think, or it's at least very difficult to cover all of these situations. I hope this answers your question.
Thanks.
Yeah, maybe related to that, so could you replace also your W by a neural network?
Yeah. Yeah. So people have done this. Yeah, sure. And there are very good approaches there. I mean, if you got WaveNet, for example, from Google, complex spectral mapping. Although, in my opinion, if you then just try to downscale, they're typically large networks. So that also has to be said. So that was maybe I didn't stress this well enough, but if you have, for example, a non-online application, you have a sound recording and you want to enhance it, there are incredibly good techniques with large networks. Yeah, great, yeah. But downscaling is just, let's now take a smaller one, doesn't always work as well, or it doesn't then generalize as well. And they're not always also online. So there are advantages of definitely just these nonlinear networks. Also, as I said, don't go to propagate this paper. There's one paper from a group in Hamburg, which also then does this nonlinear processing, also for multi-microphone speech enhancement, and really looks at the specific properties for spatial, spectral, and temporal. So best performance, go for the best network, largest network, well, maybe largest, but a very large network. But if you go to these kind of applications, at least at the moment, I would say that's not yet feasible.
Okay, thanks. Okay, there's one in the back.
Simon, thank you for the presentation, very interesting. Could you comment on the impact of reverb? When I looked at your videos, I saw the absorbers were out there, the back wall, some of them. And I'm interested in what are the challenges when it comes to these types of algorithms, especially in terms of low latency and hybrid approaches. Could you share some insights?
Yeah, thank you very much. A very good observer that the situation was, of course, not that reverberant in the scenes that I played. I would say up to a certain reverberation time, so these acoustical reflections, there are not really any issues. As you also know, I didn't focus on this talk. There are also the reverberation algorithms. So, for example, one very popular one, or very good one also is this weighted prediction algorithm. And also there, I would say you have purely model-based one. Yeah. We also worked on this, purely learning-based, and also now hybrid approaches for this kind of reverberation algorithm. So it is a challenge. I actually explicitly didn't focus on this in this talk, but I could have also given the talk actually also on the reverberation with kind of the same, I think, findings actually. But it needs to be taken into account. It's not as easy, reverberation as just noise. But I think, in my opinion, nowadays algorithms are already quite good to go to a reverberation time of 600 to 800 milliseconds.
Okay, if there are no more questions, so let's thank Simon again for the nice talk.